This is the third video for Unit 7. In the last two videos, we talked about some new trig identities, mainly the sum difference and double angle identities. And we're going to do some more interesting things with those identities once we, in this video, talk about inverse trig functions. So if you think back to when we first talked about an inverse, in order for a function to have an inverse, it has to be 1-to-1, meaning every x value goes to a unique y value. So if you think about that graphically, it means that we often say a graph passes the horizontal line test if it's 1-to-1, which means any horizontal line I were to draw in the coordinate plane, it would intersect the graph at most once if the function's 1-to-1. So if you think about all our trig functions, they all fail that. So however, we've dealt with other functions that failed that, mainly talking about the basic parabola, the parent graph y equals x squared. And that clearly was not invertible. It failed the horizontal line test, not 1-to-1. But if we restricted the domain, then we could find the inverse. And usually we restrict the domain, so we captured all the values of the range. We either restricted it 0 to infinity or negative infinity to 0. And we're going to do the same, we're going to apply the same rationale here with trig functions in order to make them invertible. So if you think of the sine function, I'm going to do a basic graph here. So the sine function, and this would be pi over 2 pi, 2 pi, negative pi over 2, negative pi, negative 2 pi. Again, clearly not invertible as is. But the convention for functions to be invertible, or rather the criteria that mathematicians came up with for to define the intervals such that the function is invertible is like but with y equals x squared. You want to make sure you're covering all possibilities for the range, but also we decided we want to cover all the acute angles, and you would like the interval for which you cover or for which it's restricted to be a continuous interval, or at least adjacent intervals. You're going to see with some of the reciprocal functions, there is some discontinuity where it's undefined. And so for sine, looking at this graph, well, the acute angles would be 0 to pi over 2. But if I go all the way to pi, I'm going to fail that horizontal line test and not cover all elements of the range. So we restrict the function from negative pi over 2 to pi over 2. So what does that mean? Well, that means, remember what it means about an inverse. The domain and range get flipped. So when I talk about inverse sine, and another notation for inverse sine is arc sine. So you can use either one of those. So whereas in the standard trig functions, the input was an angle and the output was a ratio. In this case, our inputs are ratios and our output are angles. So again, when we talked about the sine graph, the sine function, normally the domain is everything. But in order to have an inverse, think about what we did with y equals x squared. We think about, okay, y equals sine x for x between negative pi over 2 and pi over 2. So thinking about restricting that domain. And what that means is when we find the inverse, well, not to the negative x, hold on, it should be negative 1. Okay, so when we find the inverse, the domain is the output of the original, which would be the range of the original sine function, negative 1-to-1. So that's the possible ratios I can input. And the range now will be this restricted domain of the original function. And this means that if I'm doing inverse sine of any positive ratio, of course it has to be in the domain of negative 1-to-1, any positive ratio, then the output or the y values are going to be quadrant 1 angles. Whereas if I'm inputting any negative ratio, the output is going to be negative quadrant 4 angles. And remember what a function means. For every input, there is a single output. So some people often make the mistake, for example, if, say I say evaluate inverse sine of negative 1/2. They make the mistake of thinking, oh, let me give a quadrant 4 angle. Let's give 11 pi over 6. It is true that sine of 11 pi over 6 is negative 1/2, but 11 pi over 6 is not in the range of negative pi over 2 to pi over 2. You've got to give a negative quadrant 4 angle, so it's going to be, and it has to be between negative pi over 2 and 0, so it has to be, in this case, negative pi over 6. Only one answer. So these are different problems, in other words. Solving for sine x equals negative 1/2 versus solving inverse sine of negative 1/2 equals x. There's only one answer to this problem, as we stated. It's just negative pi over 6. Inverse trig stands for a function, only one output. Whereas here, thinking about the graph of sine, there's infinite places, angles, where when you take the sine, you get negative 1/2. So the solution here would be 7 pi over 6 plus 2k pi, as well as 11 pi over 6 plus 2k pi. Infinite solutions. So those are two very different problems. In both cases, you're thinking of where is sine negative 1/2, but you're restricted with inverse trig to a particular range. Okay, so that was sine. Let's now talk about, maybe I'll do cosine next. All right, so if we think of cosine, I'm going to apply a similar rationale here. So just a quick rough draw of the cosine graph here. All right, so this is pi over 2. This is pi. Oh, maybe I'll draw it up here. And got negative pi over 2, negative pi, 3 pi over 2, and so on, and then 2 pi. But we've got enough here to go off of. All right, so could I do negative pi over 2 to pi over 2? Could I restrict it in the same way? No, not 1 to 1. So remember, I want the acute, so 0 to pi over 2. And in order to continue so that into one connected interval, 0 to pi would work out great because I would get those acute angles, I'd get all the elements of the range. So we're going to, in order to be able to take the inverse of cosine, we're going to restrict the domain 0 to pi. So when I think about inverse cosine, or arc cosine of x, the domain, like sine, is the range of the original function, negative 1 to 1. And the range now, instead of being negative pi over 2 to pi over 2, it's 0 to pi. Which means that, just like we talked about with cosine, if I input positive ratios, the output is going to be quadrant 1 angles, those acute angles, where if I input negative ratios, this time you're giving me a quadrant 2 angle. So let's give an example. So if I were to do, if I said evaluate inverse cosine, let's stick with the theme of negative 1/2. You would give me just one answer, and it would be a quadrant 2 angle, and it would be 2 pi over 3. So a single answer. Okay, so yes, do you have to know these? You do. And it helps, we just did a unit on graphing, so it helps to visualize the graph, and keeping in mind that if I'm including those quadrant 1 angles, acute angles, and I need to include something adjacent to that so that it is 1 to 1. All right, so, and covers all elements of the range. Last one of the standard trig functions, let's talk about tangent. All right, so let's do a rough graph here. Remember, period of tangent is different, so this is pi over 2. I'm just going to draw one period. And undefined at pi over 2, negative pi over 2. And so tangent, I actually am not going to draw, I mean, it continues on it in the same way, but it kind of jumps out at you how to restrict the domain in this case. It's good, you're going to restrict it to negative pi over 2 to pi over 2. So in order to make this invertible, again, restricting from negative pi over 2, but I'm not going to include that because it's undefined, same at pi over 2. Okay, so when we talk about inverse tangent, the domain or the ratios I can input are everything because the range of the original function is everything. And the range is going to be negative pi over 2 to pi over 2 exclusive. So like sine, when I input positive ratios, I get quadrant 1 angles. When I input negative ratios, I'm getting that negative quadrant 4 angles. So very, very similar to sine. So for example, if I do inverse tan of negative root 3, you're going to give me negative pi over 3. So a negative quadrant 4 angle. All right, so let's just briefly talk. For the most part, the reciprocal functions match up with the standard trig functions, with one exception, cotangent. So let me just on the next page go through those. Okay, so let's do inverse cosecant. So it's going to be very similar in terms of the quadrants for the range of angles as sine. So the domain is negative infinity, negative 1, the range of the original function, and 1 to infinity. And the range is, instead of saying negative pi over 2 to pi over 2, I just am going to, it's undefined at 0. So I'm going to say negative pi over 2 to 0, union 0 to pi over 2. But it's the same idea in the sense that if it's a positive ratio, you're outputting a quadrant 1 angle. And if it's a negative ratio, you're outputting a negative quadrant 4. Secant is going to follow like cosine. So the domain, negative infinity to negative 1, the range of the original. And the range is 0. It's like 0 to pi, but it's undefined at pi over 2. It's undefined where cosine is 0. So you're either giving me a quadrant 1 if the ratio is positive, or a quadrant 2 if the ratio is negative. Last, well, cotangent, the domain, everything like tangent, the range of the original. But in order to have just a nice clean period, a nice clean interval like tangent was, the range is 0 to pi, exclusive of 0 to pi. Because if you think of the cotangent graph, it's undefined at 0 and then undefined again at pi. And it looks like this. So it's just so nice to have that as our restriction, 0 to pi. Okay, so let's do some problems with this. Okay, so there are the standard problems, which are just evaluate the following without a calculator. And it just requires you knowing, obviously, the ratios that angles are associated with the various trig functions, but also knowing the domain and ranges of the inverse trig function. So if I said something like, so evaluating without a calculator, doing something like inverse cosine of negative root 3 over 2, being able to say what that is, you have to remember, negative ratio, quadrant 2. So I would say 5 pi over 6. Or something like inverse secant of root 2. That would be a quadrant 1, pi over 4. And what if I said something like inverse sine of pi over, let's see, pi over, what if I said inverse sine of pi over 2? What would you think there? So I think this can cause confusion because you think pi over 2 is an angle, which it can be, but in this context, since it's the input of an inverse trig function, we're talking about a ratio, and the problem here is this ratio is greater than 1. So this would be no solution because the input has to be between -1 and 1, so that is out of the domain, so there'd be no solution there. So just be mindful of what is being inputted versus outputted. All right, let's do something a little bit different then. In terms of problems, what about if we did now something like, just expanding in a little bit more, still evaluate or without a calculator, if I were to do, let's see, inverse cosine of sine of 2 pi over 3. All right, well, luckily we know sine of 2 pi over 3, so this would be inverse cosine of root 3 over 2. And the inverse cosine of root 3 over 2, I'm going to give a quadrant 1 angle, pi over 6. Let's do what about this? Inverse cosine of cosine, let's see, cosine, I want to do something interesting, 5 pi over 3. Now, I see that I've got inverse cosine and cosine, so a function composed with its inverse should undo each other. So does that mean that this equals 5 pi over 3? In this case, no, because 5 pi over 3 is not in the range of inverse cosine. So it has to be, something between 0 and pi, my answer. And, well, what is it going to be? Well, cosine of 5 pi over 3, I actually can find that. And maybe in this case we'll do it. And then I'll do one where we can't find. So cosine of 5 pi over 3, in quadrant 4, cosine is positive. So cosine of 5 pi over 3 is going to be a half. And inverse cosine of a half is pi over 3. Well, what about, though, if it was something like this? Inverse cosine, oh, let's do something like, I want to do something you don't know. All right, so like 11 pi over 10. This doesn't correspond to a special angle, and could I just say this equals 11 pi over 10? Oops, no. The reason is 11 pi over 10, it's a pi over 10 greater than pi. So 11 pi over 10 is going to be in quadrant 3, where this would be pi over 10. And so my output of inverse cosine cannot be quadrant 3. Because 11 pi over 10 is landing in quadrant 3, however, I know that this ratio would be negative. So if I'm doing inverse cosine of a negative ratio, my output should be a quadrant 2 angle. So what is the quadrant 2 angle that would get the same ratio as cosine 11 pi over 10? Well, it would have that same reference angle, pi over 10, but it would be in quadrant 2. So the answer here, instead of being 11 pi over 10, it would be 9 pi over 10. So those types of problems are interesting. You have to be very careful about seeing if, does the function composed with its inverse, does it undo each other, and do I get that output that I inputted, or is the output the same as that input, or do I have to adjust that output in order to put it in the range of my particular inverse trig function? So those types of problems are interesting, and you will get some practice in the review with those, some more. How about, again, doing something different? The outer function now, instead of being inverse, what if the outer function is a regular trig? So I have cosine, say inverse sine of 3/5. Well, 3/5 isn't a ratio of one of my special angles, but I actually don't need to find that angle associated with 3/5 when I take the sine, because I can draw out, remember, inverse trig, the output is some angle. So let's draw this angle. And inverse trig tells me exactly where this angle will be. Since the ratio is positive, the angle has to be in quadrant 1 for inverse sine. So I've got 3/5. And using the Pythagorean theorem, the x-coordinate is 4, positive, because again, I'm in quadrant 1. So now I can take the cosine of this angle, and that would be 4/5. So remember, inverse trig stands for an angle, so we can often draw that angle. Okay, or we can draw that angle. Let's do something even different. What if I said, find the sine of 2 inverse cosine of, let's do -3/5. Well, I find it helpful again to see the fact that I'm taking a sine 2 times some angle here. Inverse trig the output of inverse trig is an angle. So recognizing I'm doing sine 2 times some angle, I've got to use an identity. This is going to be equal to 2 sine of the angle, cosine of the angle. So identities coming back here, the identities we did in the first 2 videos. All right, well, in order to find sine of the angle, cosine of this angle, I've got to set up the appropriate triangle. And for inverse cosine, if the ratio is negative, I'm drawing my triangle in quadrant 2. And the x will be -3, the hypotenuse is 5, and the y value will be +4. So the sine of this angle will be 4/5, and the cosine is -3/5, and this will get me -24/25. You can do a similar type of problem, and we've had some where you have to use a sum difference identity. So for example, instead of me saying sine of 2 times some angle, I could have said evaluate sine of inverse cosine -3/5 plus inverse tangent of -1/5, for example. And this, again, just recognizing what you have is so important. This stands for an angle, I'll call it alpha, and this stands for an angle, I'll call it theta. So you're doing sine of some angle plus another angle, so you're gonna have to use the identity. Sine does not distribute across addition. Sine can't be anything by itself, except the word sin, so don't do that. All right, so you've just got sine alpha cosine, sine theta cosine alpha plus sine alpha cosine theta. And in order to actually do this, I need to draw the 2 triangles for those angles. So cosine is inverse cosine. If the ratio is negative, I'm in quadrant 2, so -3/5. So the same triangle that I did in the previous example. And so we'll just call this one theta, and this other one alpha. So let's do, if tangent, input of inverse tangent is negative, I'm talking about a negative quadrant 4 angle. So negative where y is negative. And using the Pythagorean theorem, root 24 or 2√6. And this one's standing for alpha. So now just filling in the different ratios, sine of theta is 4/5. Cosine of alpha is 5/2√6, plus sine of alpha is -1/2√6, and cosine of theta is -3/5. All right, so what do we got here? So we got 20/10√6 plus 3/10√6. And you could course, you could combine the numerators in this case because the same denominator, so 23 over 10 root 6, and you could rationalize it as well. But you get the idea there with those types of problems. So lots you can do once we talk about inverse trig here. And, but yes, it's so important to keep in mind those identities too. Okay, that's it for this video.